Welcome to Session 8. Last time, learning from the prompt appeared somewhere between 1 and 100 billion parameters, and nobody had predicted it. Today the question is whether anything about scale can be predicted in advance, because a training run isn't an experiment you get to repeat. Before we touch a single number, let's get our bearings. Look at what the last 6 sessions actually nailed down. Words became vectors. Attention replaced recurrence. The transformer block became the standard unit. And 2 sessions ago, predicting the next token turned out to be enough to teach a model to follow instructions from its prompt. But the architecture itself never told you 3 things: how many parameters to use, how much data to train on, and how much compute to spend getting there. Those 3 slots are still wide open, and nothing we've built so far fills them in. Give them names. N, the parameter count. D, the training tokens. C, the compute. Every one of Session 7's models, GPT-1, GPT-2, GPT-3, was really just a different choice of these 3 numbers. And whatever you choose for N, D, and C decides what you actually get out the other end, how good the model's predictions are, and which abilities show up at all. That's today's question. Can you know what you'll get before you spend the money? Let's make that question concrete with a real number. What you're looking at is GPT-3's actual training run, drawn to scale on a real calendar. Notice what was fixed before it started. 175 billion parameters, 300 billion training tokens. And that combination costs about 3 times 10 to the 23rd floating point operations, flops for short. One flop is just 1 multiply or 1 add. We'll come back to that 6 per parameter per token rule properly in a few slides. For now, just notice that a compute number this big is what you get when you multiply 175 billion by 300 billion. Now, that number isn't one machine running for months. It's thousands of GPUs running in parallel for the whole length of that bar. Millions of dollars by public estimate. OpenAI never published the exact bill, and you won't see this figure claim to know it either. 3.5 months. Once. You don't get a second try at this scale, and you don't get to run it twice to check your work. So, here's the actual problem hiding inside that bar. Look at that red line. Everything that decides the outcome, parameters, tokens, compute, gets fixed right there before a single gradient step has run. And the only place you find out whether those choices were any good is all the way over here, 3.5 months later. 1 attempt. No revisions in between. There's no arrow back. You can't spend a little bit to find out what a big run would do. And once you've spent the big run, you can't take it back and try again. That's the problem this whole session is about solving. How do you commit a budget in advance when the only way to test your choice is to already have spent it? Here's what you'll walk away with today. First, you'll be able to explain exactly why that one-way arrow exists, in your own words, to someone who's never seen this problem. Second, you'll be able to take a handful of cheap runs and use them to predict the loss of a run you haven't afforded yet. Third, given a fixed compute budget, you'll be able to actually split it between parameters and data with a real formula, not a guess. And fourth, when someone shows you a chart where a model's ability jumps out of nowhere, you'll be able to tell whether that's real or whether it's the ruler doing the jumping. Before we go looking for an answer, let's be precise about what an answer would even have to do. First requirement: whatever pattern we find has to show up on runs we can actually afford. Because the whole problem is that the frontier run is the one we can't use as a test case. Second, that same pattern has to keep holding as you go from a handful of cheap runs all the way out to the frontier run, across orders of magnitude, not just locally. And third, it can't just predict a single number. It has to tell you how to spend the budget, how much goes to parameters, and how much goes to data, because that split is a decision you make before the run starts. Put those 3 together, and that's the actual target, not just a loss number. Right, let's get into it. Let's run the cheapest experiment there is. Just plot what you actually see. 6 real runs from 1 million parameters up to 1 billion, all comfortably affordable. Loss falls as the models get bigger, which is what you'd hope. Fit the obvious thing to it. A straight line. Now, follow that line down and it hits zero loss at a model size still inside the same axis. Zero loss. A model that never makes a mistake. That's not a real prediction. That's a straight line telling you it doesn't understand the shape of this problem at all. And the run you actually care about, GPT-3's 175 billion parameters, is 55 times further right than this entire axis even reaches. A straight line fit on linear axes has nothing useful to say about it. So the straight line guess failed. But we're not done with those 6 runs yet. Same 6 points, back on linear axes, here's the fix, and it's the single most important move in this whole session, so stay with me. Watch the x-axis, parameters, stretch logarithmically instead of linearly. Equal distances now mean equal multiples, 10 times, 100 times, 1,000 times, not equal amounts. Now do the same thing to the y-axis, the loss. Watch what happens to the same 6 points you just saw scattered on linear axes. They fall on a straight line, not approximately, genuinely, across the whole range. That's not a coincidence, and it's not a coincidence about these 6 points specifically. It holds for runs like this generally. A straight line in log-log coordinates has a name for its slope, an exponent. That number is the whole rule, compressed into one constant. You might be wondering if changing the axes is just a trick to make messy data look tidy. It isn't. The axes don't change what the runs measured, only how evenly we space the numbers, and the points were free to land anywhere on this grid. They chose a line. And because the line is straight all the way out, you can extend it, honestly, out to 175 billion parameters, a run that hasn't happened yet on this axis. That's the trick. Not guess a curve. Find the coordinate system where the guess doesn't need to be a curve at all. Here's why that works. Written out. A straight line in log-log space is log loss equals log of a constant, nc, minus alpha times log n. That constant is just a reference scale baked into the fit itself. Nothing more exotic. Rearrange that, undo the logs, and you get loss as n to the power of minus alpha times that same constant. A straight line on a log-log plot is a power law. In other words, that's the whole identity, just seen from 2 different angles. Kaplan and his co-authors at OpenAI published exactly this shape in January 2020 in a paper called Scaling Laws for Neural Language Models. And it's the reason the field can talk about model scale quantitatively at all. Let's push on this a little further. Now, that shape we just found for parameters, it isn't a one-off. Hold the model size fixed and vary how much training data you feed it instead. Same picture, a straight line in log-log space. Hold the ratio fixed and vary total compute instead. Same picture again. 3 completely different things you could scale up, and all 3 obey the identical mathematical shape. Loss equals a constant over the scaled quantity raised to some power. That's what makes this a law, and not 3 separate lucky coincidences. It's Kaplan and colleagues' central finding, and it held across 7 orders of magnitude of runs when they published it. Notice, though, this only tells you the shape each curve takes when you scale one thing at a time. It doesn't yet tell you what to do when you have to scale all 3 together on one fixed budget. Now, for something that actually happened, not just theory. These axes come straight from OpenAI's own report. You're seeing them exactly as they were published, unlabeled y-axis and all. Here's what they did. OpenAI trained a ladder of small models, using 10,000 times less compute than their real target. They fit exactly the kind of power law you just watched us derive, and extended it. And when they finally trained the real thing, at 10,000 times the compute, its actual loss landed almost exactly where the small run fit said it would. That's GPT-4, predicted from runs a fraction of its size before it existed. This is the OpenAI GPT-4 technical report, 2023, and it's the concrete case that makes everything we just derived worth caring about. Okay, new picture. So the law tells you loss falls predictably with scale. But scale isn't one setting you turn up. It's a budget you need to split between 2 things. Picture your compute budget as a rectangle. One side is how many parameters you choose. The other side is how many tokens you train on. The budget is the area of that rectangle, not either side alone. Where does the 6 come from? Every parameter needs roughly 6 floating point operations per training token, 2 for the forward pass, 4 for the backward pass. That's the whole constant. Now, here's the part that matters. The same budget, the same area, can be a tall, thin rectangle, few tokens, huge model, or a short, wide one, many tokens, small model. Same cost, completely different model. Notice that every point on this curve costs exactly the same. Somewhere along it sits the best place to be, and finding that spot is the question the rest of this act answers. 6, N, D. 3 symbols, and now you know what all 3 mean. 6 operations per parameter per training token. Put simply, a compute budget is an area, and this identity is just how big that area is. This is the identity every plot for the rest of today's session is built on. So, where on that curve should you actually sit? So, given a fixed budget, how should you split it? Kaplan's own paper answered this question too, not just the loss law. Here's his recipe. It leans heavily toward parameters. Worked out as an exponent, parameters grow with compute to the 0.73. Tokens only to the 0.27. Spend most of a bigger budget on more parameters, comparatively little of it on more data. Remember, GPT-3 itself, 175 billion parameters on 300 billion tokens, was built to this recipe. That's not a coincidence. OpenAI followed Kaplan's own guidance. Written out as a ratio instead of an exponent, GPT-3's own numbers come to about 1.7 tokens of training data for every parameter. Hold on to that number, because the correction coming up moves it a long way. There's a catch, though. Lean that hard on parameters, though, and something has to give. Let's watch it happen directly. Hold the training data fixed at 300 billion tokens, GPT-3's own number, and just keep growing the model. The curve doesn't keep falling. It flattens toward a floor. Past some point, more parameters stop buying you anything, because the model has already learned everything 300 billion tokens of data has to teach it. At GPT-3's own size, 175 billion parameters, look how close the curve already sits to that floor. There isn't much loss left to buy with more parameters alone. You might be thinking, fine, then grow the data along with the parameters. Exactly right. And that's the only thing that actually moves the floor, which means Kaplan's parameter-heavy split was leaving something on the table. This next picture is the one the whole correction rests on, so we'll take it slowly. Fix the total compute budget completely and ask, of every way you could split it between N and D, which one is actually best? Look at these runs, all costing the identical amount of compute, just at different points along the split. Plotted against model size, they trace a U. Too few parameters, undertrained on the model side. Too many, undertrained on the data side, exactly what you just watched happen. Somewhere in the middle is a minimum, the best model size for this exact budget. Now repeat it at 10 times the compute. And again, at 100 times the original budget. Connect the bottoms of those 3 U's, and that line is the actual answer, the best split as a function of total compute. This is Hoffman and colleagues' isoflop method, DeepMind 2022, and the U-shapes here are schematic, standing in for the paper's own measured profiles. Hang on, this one's worth a second look before it scrolls past us. Every remaining slide in this act leans on this picture, so let's make sure it's actually legible. Remember, one point on this plot is one entire training run, a specific model size, trained to completion, at this one compute budget. One curve is every run you could have trained at that same budget, differing only in how you split it. And follow the line running under all 3 curves, connecting their lowest points. That's the envelope, not a run, a rule. It's where the minimum of the U sits, as the budget itself changes. So why did Kaplan's own recipe get outperformed by this envelope? It comes down to one quiet assumption buried in how the runs were trained. Here's the thing. Every training run follows a learning rate schedule, a plan for how fast the model updates. and that plan decays to nothing by the end of the run. Kaplan's runs all used a schedule set for one fixed length. Now take a run that sees 4 times as much data. It needs to run 4 times as long, but the schedule was never built for that. For most of its length, that run is training with a learning rate that's already decayed to almost nothing. That quietly penalizes exactly the runs Chinchilla's answer would want you to prefer. The ones that lean more heavily on data. It's not that the loss law from 3 slides ago was wrong. It's that the allocation experiment built on top of it had one flawed setting. Hoffman and colleagues fixed exactly this. Rescale the schedule to match each run's own length before comparing them. Once that's done, the U-curve's minimum moves, and that's the recipe correction coming up next. So what actually happened next? With the schedule fixed, here's the corrected answer, and it's worth putting right next to Kaplan's. That's the path Kaplan's own recipe walks as the budget grows, parameters climbing much faster than data. And that's the one Hoffman and colleagues actually found once the schedule was fixed. Parameters and tokens growing together at a fixed ratio. 3 real models placed on the same plane. Notice how far GPT-3 and Gopher sit from the corrected line, and how close Chinchilla sits to it. Because Chinchilla was built specifically to test this correction. Written under Kaplan's own exponent from a few slides back, so you can watch the correction happen. Not a totally different theory, a changed ratio. About 20 tokens of training data for every parameter. In one sentence, parameters and tokens grow together, not one racing ahead of the other. That 20-to-1 rule, can you actually use it? Let's find out with a real calculation. Say you're handed a budget of 10 to the 23rd flops, roughly a third of GPT-3's own compute, and told to spend it optimally. How many parameters should you train, and how many tokens should you train them on? Work it out before the next slide. Start from the 2 things you actually know, the compute identity and the 20-to-1 ratio, both written whole before we touch a single number. Now you substitute the budget in for C and the ratio in for D. Multiply it out. 6 times 20 is 120, and you're left with the budget equal to 120 times $n squared. Divide both sides by 120, and take the square root. That's about 29 billion parameters. 20 tokens for every one of those parameters puts you at roughly 580 billion training tokens. 29 billion parameters, 580 billion tokens. That's the compute optimal answer. Now run Kaplan's own recipe at this exact same budget instead. It puts roughly 2.5 times more weight into parameters than this, and correspondingly less into data. That's exactly the imbalance the last few slides walked through. Let's see the difference in practice. Here's what that correction actually buys you, in a real comparison, not a hypothetical. Look at Gopher first. DeepMind's own 280 billion parameter model, trained the Kaplan way on 300 billion tokens, scored 60% on the MMLU benchmark. Now compare Chinchilla. Trained at the exact same compute budget, but following the 20-to-1 rule, it scored 67.6, a real gain at identical cost. And Chinchilla did it with 70 billion parameters, 4 times fewer than Gopher's 280 billion. It spent the difference on roughly 4.5 times as much training data instead. 1.4 trillion tokens against Gopher's 300 billion. Same compute, smaller model, better score. That's Hoffman and colleagues' own headline result, table 6 of their paper. There's one question still hanging over all of this, and you might have already asked it yourself. Did the field actually listen? Here's the impact. Every major lab recut its recipe after this result. 20 tokens per parameter became the default starting point, not an obscure finding in a paper. And then, some labs went further, on purpose, and kept going. The original Llama 7B already sat past Chinchilla, at around 150 tokens per parameter. A little over a year later, Llama 3's 8 billion model pushed that past 1800. Both were deliberately trained on far more tokens per parameter than Chinchilla's own rule suggests. Why? Because Chinchilla's rule optimizes training cost. Once you're going to serve a model to millions of users for a year, inference cost starts to matter more. A smaller model that's cheaper to run every single query can be worth training a lot longer, worth pushing even further as that inference bill keeps growing. Here's a harder one. Everything so far has been about loss. One number falling smoothly and predictably as you scale. Now ask a harder question. Does every ability the model has scale the same smooth way? Take a genuinely simple task, 3-digit addition, and look at how a family of models scores on it as compute increases. For 3 whole decades of scale, nothing. 4 runs in a row, every one of them at 0. Watch 4 more runs land. 3 of them barely move. 0.5%, 2%, 8%, still close enough to nothing. Then, the last one jumps to 80. Not gradual, a cliff. Loss over this same range was falling the whole time, smoothly, exactly as the power law predicted. But this particular ability sat at 0 until a threshold, then rose sharply. Whatever's happening here, it isn't the same story we've been telling for the last 15 slides. Let's widen the lens. This isn't a one-off with addition. Now look at a second task. Different benchmark entirely. Same shape, flat, then a jump, but at a different point on the scale axis. Follow a third with its own chance baseline, because not every benchmark starts at 0%. Same shape again, flat near chance, then a rise. Notice, 3 genuinely different tasks, and their thresholds sit 2 whole decades of compute apart from each other. These aren't the same event happening 3 times. They're 3 independent abilities, each turning on at its own point. Here's the name for it. Wei and colleagues, publishing across Google, Stanford, and DeepMind in 2022, called this pattern emergent abilities. Present at chance until a threshold, then rising sharply, unpredictable from the smaller runs, the way loss isn't. Here's an honest objection to what we just saw, and it's the one this session needs to end on. Score those same addition runs differently. Instead of asking, did it get the whole answer right, ask, what fraction of individual digits did it get right? Same runs, same models. Look at the curve now. Smooth, rising steadily, no jump anywhere. Now you put the original scoring back beside it. Exact match, right or wrong on the whole multi-digit answer. Look, one underlying capability, 2 ways of grading it. A cliff under one ruler, a smooth climb under the other. Follow the same 3 runs across, from the smooth curve to the cliff, and you can see exactly where the metric manufactures the jump. Here's why. If each of the k digits is right with probability p independently, then getting the whole answer exactly right needs every digit right, probability p to the power k. Raising a number less than 1 to a power makes it fall fast, faster than the number itself falls. That's assuming each digit's error is independent of the others, which is a real assumption, not a certainty. And it's worth remembering exactly, because it's the kind of thing this session is teaching you to notice. Let's check ourselves again. Same move, real numbers this time. Say a model gets 90% of individual digits right on a 5-digit sum. What exact match accuracy does the benchmark actually report for that model? Work it out. Okay, step by step. Start from the identity itself, whole, before any number goes in. Follow it, 90% per digit, squared for 2 digits, already down to 81%. To the 4th power, for 4 digits, and you're already under 66%. To the 5th power, for all 5 digits, 59%. 90% per digit becomes 59% on the benchmark. A model that's right 9 times out of 10 on any given digit is wrong on the whole answer more than 4 times out of 10. Now put that next to 2 neighboring values. 70% per digit becomes 17% exact match. 99% per digit becomes 95% exact match. Move smoothly from 70% to 90% to 99% per digit, roughly evenly spaced. And the benchmark reports 17, 59, 95. That climb from 17 to 59 to 95% is the cliff you saw 2 slides ago. Not a new ability switching on. Arithmetic, raised to a power. One identity, written across both panels. The smooth curve on the left and the cliff on the right are the exact same underlying numbers, read through two different rulers. So where does that honestly leave us? Not everything's a mirage, and not everything's real. Three separate claims, three separate verdicts. Loss, falling smoothly with scale, that's measured directly across 7 orders of magnitude of real runs. That one's solid. Now the second claim, the one you just watched form, capability jumps sharply at a threshold. That one depends on the ruler. Sharp under exact match, smooth under per token accuracy. Not false exactly, but not metric independent either. And here's the claim that survives, regardless of which ruler you pick. You still can't say in advance which specific ability a bigger run will unlock, or exactly when. That uncertainty is real under either metric, and it's the reason every frontier training run is still in part a gamble. The whole session, in one chain. Compute predicts loss. That arrow, the law does. Loss predicts capability. Nothing we've got does that arrow reliably. Yet. Schaefer, Miranda, and Coello made this exact argument in 2023 in a paper that won an Outstanding Paper Award at NeurIPS. Their point wasn't, emergence isn't real. It was check your ruler before you believe your cliff. Let's close the loop we opened at the very start of this session. We started here. One-way commitment. Choose your parameters, your data, your compute, and only find out if you were right months later with no way back. You can't undo that one-way arrow. But you're no longer walking into it blind. You can size a run before you spend it, and fit the law that tells you roughly what loss it'll land on. You can split the budget between parameters and data with an actual rule instead of a guess. And you can read a headline about a model's sudden new ability with the right amount of skepticism. Before we close, there's one question today's law never even claimed to answer. 2 boxes on screen, and the same word is stamped on both of them. Public. Keep your eye on that word. Think about it. The scaling law is public. The transformer architecture is public, and every one of these 5 labs had access to both. Claude, GPT, Gemini, Llama, DeepSeek. And yet, these models behave nothing alike. I'm not going to draw you a scoreboard here, because how they actually compare is genuinely next session's work, not something to invent on this slide. The law fixes how much compute buys you in loss. It never touched what data you train on, how you align the model's behavior, how you fine-tune it, or how you deploy it. Every one of those is a decision made independently by 5 different labs holding the identical public recipe. Let's see where we've got to. 7 sessions behind us now. Language, vectors, sequences, attention, the transformer, BERT, and GPT. And session 8 is where we're standing. The law that tells you how big to build, and the honest limits of what it predicts. 6 sessions still ahead. We're at the hinge between the architecture stretch and the real-world half of the course, and next time is exactly where that hinge turns. One last thought before we close. The law fixes how much to buy. It never said what to build. Every lab had the same law, the same architecture, and the same public recipe, and yet they shipped models that behave nothing like each other. Next session, we go find out why. The differences are decisions, not accidents. And in the lab, you're not going to reproduce today's slides. You're going to run this yourself. Part 1. You run a ladder of small training runs yourself and fit a real power law to your own points, the same log-log move from earlier today, on your own data. Part 2. You use C is approximately 6 times N times D to derive the compute optimal split from your own fit and set it against both Kaplan's and Chinchilla's published splits. Part 3 is the one that makes it a workshop, not a repeat of the lecture. You're told you'll be serving this model for a year, not just training it once. Add that cost into the objective, and watch the optimum move away from Chinchilla's rule, the exact decision Llama made, except this time, you're the one rederiving it. And the challenge? Take 1 tasked runs and score them under exact match and under per token accuracy, and produce the mirage result yourself on your own numbers.